In today's lecture, we are going to see a very important concept, and it is actually the concept of symmetry operations in crystals. When you say symmetry operation, definitely a question arises in your mind. What is this symmetry operations? How many types of these symmetry operations are possible? Actually, a symmetry operation is defined like a operation which leaves the crystal environment invariant. It means whenever a symmetry operation is performed on a crystal lattice, the lattice remains invariant. Lattice does not change. So you can say that it is an operation which transforms the crystal into itself. It means after any symmetry operation, the crystal does not change. Basically, there are four types of symmetry operations. In other words, you can say there are four basic symmetry operations. And these four basic symmetry operations are translation, rotation, reflection, and inversion. Actually, these are the four basic, or you can say fundamental symmetry operations in crystal. But apart from this, when we will combine two or more symmetry operations, we get new symmetry operations too. So after combining these basic symmetry operations, we also get more three symmetry operations, and those three operations are rotation, inversion, screw, and glide. Now, after getting the idea of what is this symmetry operation, what are different types of symmetry operation, I would like to explain each and every symmetry operations in detail. Okay? Actually, in this present lecture, we will see only two basic symmetry operations, and those will be translation and rotation. And the remaining symmetry operations we will discuss in the next part of this lecture. Okay? So let us start to know what is translation symmetry operation. Actually, this translation symmetry operation is defined as a symmetry operation actually after which the lattice point, if you consider that there is a lattice point whose position vector with respect to an arbitrary origin is r, and when you combine this r with the translation operation t, you get the new lattice point whose position vector is r dashed. Okay? But if, when viewed through this r or r dashed, the crystal appears identical, then we say that we have performed a translation operation. So you can say that a crystal is said to possess translational symmetry if the translation of the crystal from the lattice point r under the lattice translation vector operation t gives another point r dashed which is exactly identical to r. Okay? So we simply say that r dashed is equal to r plus t, where you have seen in the previous lecture that this translation vector operation t is defined by n1a plus n2b plus n3c, where you know these n1, n2, n3 are actually the integers, and a, b, c are primitive translation vectors. Okay? So this is a very simple idea of translation symmetry and translation symmetry operation, and I hope you have understand what is this translation symmetry operation. Now actually the second symmetry operation, which is called rotation symmetry, this is a very important concept, and we will learn something more in this rotation. Actually this rotation symmetry operation will be asked to you in your examination in short answer type question, and also in the examination like civil services, it is asked several times. Okay, so let us see what is this rotation symmetry operation. In fact, a lattice is said to possess a rotation symmetry rotation by an angle theta about an axis or a point in a plane lattice which transforms the lattice to itself. It means if you rotate the crystal lattice about a point or about an axis through, let us say, an angle theta, and the lattice does not change. It means at the new position after rotation the same lattice appears, then we say that the lattice has a rotation symmetry axis. Okay. Now you know, if a lattice will be rotated by 2 pi, then it is obvious, it is trivial that after 2 pi rotation the lattice remains invariant. It is trivial. So if in general we make a rotation by an angle theta, and after this rotation theta the crystal lattice remains invariant, then definitely this 2 pi must be an integral multiple of theta. Okay, because after 2 pi rotation, you know, when we rotate a point by 2 pi the same point will appear. Okay, similarly after 2 pi rotation the lattice remains invariant. So if in general or in arbitrarily you say that we rotate the lattice by an angle theta but the lattice remains invariant, in that condition you can say that this angle theta this 2 pi must be an integral multiple of the angle of rotation theta. So you can write n theta equal to 2 pi, and therefore the angle of rotation theta, that will be equal to 2 pi over n. Actually here n, you know, this has only integral value like 1, 2, 3 and so on. And this number n, which has only integral values, this is actually known as multiplicity of axis. What is called n? N is called multiplicity of axis. Okay. Now let us see. We will see later on in detail that actually all values of n are not possible. The values of n which are possible, those are actually 1, 2, 3, 4 and 6. It means you can say that n cannot be 5, n cannot be 7, n cannot be 8 and so on. Because if the lattice has to compete with the requirement of translational symmetry, then it can be proved easily, which we will see just now, that this n will possess only these five discrete values, and these values are 1, 2, 3, 4 and 6. Okay. Actually the value, if the crystal has this value of n corresponding to any rotation, then it is the crystal is said to be n-fold rotational symmetry. The crystal has n-fold rotational symmetry. Okay, so you can say that a crystal has one-fold rotational symmetry, which does not mean any rotation, or it may have two-fold rotational symmetry, three-fold rotational symmetry, four-fold rotational symmetry, and six-fold rotational symmetry axis. It means the crystal has not a five-fold rotational symmetry axis. It cannot have a seven-fold or eight-fold or nine-fold rotational symmetry. The crystal has only the two-fold, three-fold, four-fold and six-fold rotational symmetry. How we can say this? We will see the proof just now, but before that, let us see something more, some important facts in this regard. I have mentioned it here. You can see that this n cannot be equal to 5, 7, 8, etc. It means the crystal cannot have 5, 7, 8 fold etc. exchange of rotational symmetry. For example, if you consider that the crystal has 6-fold rotational symmetry, it means n will be equal to 6, and then what will be the angle of rotation theta? As you have seen that theta is equal to 2 pi over n, so you can say that if n is equal to 6, then actually theta will be 2 pi over 6, which means this is pi by 3. Okay, if n is 6, then theta will be equal to pi by 3, and that means 60 degree. It means the lattice repeats itself with a minimum rotation of 60 degree. So if you say that a crystal has 6-fold rotational symmetry axis, what does it mean? It means the crystal lattice repeats itself after a minimum rotation of 60 degree, as you can see in this figure. Here, in fact, a plane lattice has been shown in this figure, and the rotation is taking place about the point O, or an axis passing through O, and this figure represents the 6-fold rotation about point O in 2 dimensions or in a plane. Actually, a regular hexagon you can take is a common or a competent example of 6-fold rotational symmetry. You can see, if you take a lattice in the form of a regular hexagon, as I have shown in this figure, this is an appropriate example of a lattice with 6-fold rotational symmetry. Okay. Now we will see the proof of the fact that how one can say that 5-fold rotational symmetry does not exist in a crystal. This is a very important fact, and as I have told you, you will be asked in your examination in short type of question, or particularly in civil services examination, that you have to prove that a crystal does not have 5-fold rotational symmetry, or 7-fold rotational symmetry, or 8-fold rotational symmetry. So how we can show this? Let us see the proof. For this, we consider a linear lattice. You can see on this line I have shown these dots, or small spheres, which represent actually the lattice points. So at point X, P, Q and Y there are lattice points. And we also consider that A is the lattice constant, or you can say this is the distance between 2 successive lattice points. So distance between P and Q is equal to A. Okay. We actually consider here there is n-fold rotational symmetry, and we rotate this vector Px in clockwise sense by angle theta. Okay, so that this point P is rotated to the point P1. So after rotation P moves to P1, so you know this distance will remain same. So this PP1 will be also equal to A. Okay. Similarly, when the vector Qy is rotated, the lattice point Q is rotated to this new position Q1, and so this Q1 will be also equal to A. This is actually the separation between the 2 successive lattice points. Okay. Now, as you know from the definition of symmetry operation, that after any symmetry operation, the crystal environment remains invariant. So definitely, in accordance with this definition, this P1 Q1 line must be parallel to PQ and its length must be some integral multiple of PQ. Okay? According to the definition of symmetry operations, since after symmetry operations we know the crystal remains invariant, so definitely the new positions P1 and Q1 of the lattice point when will be joined, that joining line must be parallel to PQ and the length of P1 Q1 must be some integral multiple of PQ. Okay? So you can say that this P1 Q1, this must be equal to integral multiple of A, because A is the separation between P and Q, where M you know is an integer. M is an integer. This may be 1, 2, 3, 4 and so on. Now see the figure. If this angle is theta, you can see the figure. This angle will be also theta and this angle will be also theta, because P1 Q1 is parallel to this PQ and the lines PP1 and QQ1 intersect them. Now, from the geometry of figure, our aim is to find the length of P1 Q1. And from this figure, you can see this P1 Q1 will be equal to what? This will be P1R plus SQ1 and plus RS. But RS is also equal to A. RS is equal to A. You can see the figure. Okay? And from geometry of figure, you can find what will be this P1R or SQ1. From figure, you can say cos theta will be equal to what? This will be P1R divided by PP1. And so this P1R is equal to what? This is PP1 cos theta. But PP1, you know, this will be equal to A. So this is A cos theta. And similarly, you can also find that this SQ1 is also equal to this much. So when you will substitute these values in this relation, that is P1 Q1 equal to P1R plus SQ1 plus RS, then what will be your result? I have calculated it, you can see. Actually, here you can see I have made the same calculation here, that cos theta equal to this much, and so this P1R is equal to A cos theta, and so SQ1 is equal to A cos theta too. So P1 Q1, this will be P1R plus SQ1 plus RS as you have seen in the figure. But P1R and SQ1 both are equal to A cos theta. So after summing these, you will get 2A cos theta and RS, which is equal to A. Now, you have seen that this P1 Q1 must be an integral multiple of A. So, instead of P1 Q1, I have written here MA. So, this MA is equal to A times 1 plus 2 cos theta. Now, this A and this A will cancel out, and you can say that 1 plus 2 cos theta is equal to M. And therefore, cos theta will be equal to M minus 1 divided by 2. Okay? M minus 1 divided by 2. Now, we will find what will be actually the value of the number of rotation, that is when you say theta equal to 2 pi divided by n, then n will be equal to 2 pi by theta. Okay, 2 pi by theta. We will actually obtain the value of n. What are the possible fold of symmetry? Okay. Now you know, since cos theta possesses value between minus 1 and plus 1, it means you can say that the modulus of cos theta is always less or equal to 1. So this m will have only those values for which this condition will be satisfied. It means you can take the value of m, only those values of m for which cos theta is not less than minus 1 and not greater than 1. Now, you have to take only those values of m for which cos theta will lie between minus 1 and plus 1. And you can see what will be actually those values. Actually, when you say that modulus of cos theta is less or equal to 1, then you will see just now that in this condition, m can have only these values. M may be 3, it may be 2, it may be 1, it may be 0 or may be minus 1. Except these values, if you will take any another value of m, cos theta will not lie between plus 1 and minus 1. For example, if you take, let us say, m equal to 4, what will be then this cos theta? You can see taking m equal to 4, cos theta will be equal to what? This will be 4 minus 1 divided by 2, which is 3 by 2, and this is greater than 1. So this is not possible. So the possible values of cos theta will be only when we take m equal to 3, 2, 1, 0 or minus 1. Only then this condition will be satisfied. Now let us see, when m is equal to this much, then what will be theta? And if you know the angle of rotation theta, the corresponding value of n you can easily find. As you have seen, cos theta is m minus 1 divided by 2. When you will take m equal to 3, let us see, cos theta will be 3 minus 1 divided by 2, that is cos theta will be 1. And if theta is 1, you know, if cos theta is 1, you know theta will be either 0 or 360 degree. So you have to take actually 360 degree because 0 means no rotation, but here we have to make a rotation. So when the crystal will be rotated by 360 degree, then what fold of symmetry will the crystal have? You can see in this condition n will be equal to 2 pi by theta, that is 360 divided by 360, that is 1. So in this case we simply say that crystal has one fold symmetry. It is not actually stated, because when you say one fold symmetry it means no rotation. Okay. Now let us take another value of m, which is 2. When you take m equal to 2, cos theta will be 2 minus 1 by 2, and this is 1 by 2, and so theta you know will be 60 degree. And corresponding to this theta, n will be 360 by 60, which will be equal to 6. So in this condition, the crystal will have 6 folds rotation symmetry axis. Now the third possible value of m is 1, and for this cos theta will be equal to 1 minus 1 by 2, that is 0, and so theta will be 90. And if theta is 90, what is n? N will be this much, this is 360 by 90, that is 4. So in this condition the crystal will have 4 fold symmetry axis. Okay. The fourth possible value of m is 0, and in this condition cos theta will be 0 minus 1 by 2, this is minus 1 by 2, and so theta is 120 degree, and corresponding to this n is equal to 360 by 120, this is 3, and the crystal will have 3 fold symmetry. Okay. And finally for m equal to minus 1, cos theta will be equal to minus 1, and theta is 180 degree, and n is equal to 2. So the crystal will have 2 fold symmetry. So you can see from here that the crystal will have only 2-fold symmetry, 3-fold symmetry, rotational symmetry, 6-fold rotational symmetry, and 1-fold rotational symmetry, not 5-fold rotational symmetry. Similarly, we can see that the crystal will have not 7-fold rotational symmetry, 8-fold rotational symmetry. Only the crystal has these 2-fold, 3-fold, 4-fold and 6-fold rotational symmetry, and you can easily say that a crystal has not 5-fold rotational symmetry which is compatible with the translation symmetry. So I have mentioned it here, you can see the 5-fold rotation is not permissible. Similarly, other rotations such as 7-fold, 8-fold are also not permissible. So I think you have clearly understand these two types of symmetry operations, and particularly how we can explain that a crystal does not have 5-fold rotational symmetry. Okay, and as I have told you earlier, that in the second part of this lecture we will deal with all the remaining symmetry operations in crystals. So thank you very much.